Welcome to this introductory video for Module 4B. As typical, we start with an engineering disaster to review. On March 24, 2001, a large portion of the third floor of the Versailles Wedding Hall collapsed in Jerusalem. 23 people fell to their deaths through 2 stories, while another 356 were injured to varying degrees. The engineers involved in the construction of the hall were found guilty, along with the owners of the hall, of causing death by negligence, with prison sentences given to several of them. The initial design issue was identified as lightweight coffered concrete floor systems. It was discovered that the third story was under-designed for the actual live loading. With the Versailles Wedding Hall collapse in mind, we can appreciate the necessity of looking beyond simply the applied stresses on a system and determining the worst-case stresses. In systems with only a single load, the applied stress may actually be the worst-case stress. However, in more complex systems, this is not the case. Thus, we need to look at all the stresses, the types of stress, and the direction of the stress relative to our coordinate system. That is why we use stress elements. Common stresses that may be present in a given application include direct or axial stress, that is F over A, bending stress, MC over I, torsional shear stress, T over Q, and transverse shear stress, VQ over IT. In the diagram shown, we have identified 2 points, point A and point B. Based on the system loading, each location will experience different stresses. Thus, we need to create a separate stress element for each location. At point A, the stress element reflects the maximum transverse shear stress. It also will see torsional shear stress, but it will not see any bending stress. At point B, bending stress and torsional shear stress are present, but the transverse shear stress is 0, and therefore not included on the stress element for point B. As engineers, we need to determine which location will see the highest stress and adjust our design accordingly. At point B in the previous example, we have the bending stress and torsional shear stress. However, because these stresses occur in different ways, they cannot be directly added together. The bending stress is normal to the stress element in the X direction. The torsional shear stress is along the face of the element in the XY plane. Another consideration is that if we are able to rotate the stress element, we can find higher or lower values for bending stress and torsional shear stress based on the orientation. And the maximum for each type of stress do not occur at the same angle of orientation. Christian Otto Mohr was a German civil engineer who developed a graphical method of stress analysis known as Mohr's circle, which allows us to determine the maximum normal and shear stress at a given point, taking the orientation of the stress element into account. Mohr's circle is simply a graph of the normal and shear stresses. The x-axis is the normal stress, and the y-axis is the shear stress. The center of Mohr's circle is always on the horizontal axis. Where the circle crosses the horizontal axis tells us the maximum and minimum normal stresses. Where the diameter lines up to the vertical axis tells us our maximum and minimum shear stress. To execute Mohr's circle, we start with our stress element setup. We use this formula to calculate the center of Mohr's circle. It involves the average of the stress in the x and y directions. We locate that center on the horizontal axis. The radius of Moore's circle is equal to the square root of the quantity sigma x minus sigma y over 2 squared plus tau xy squared. With the radius calculated, we can take a compass, set the radius distance, locate the compass at the center of Moore's circle, and then swing the radius all the way around to create Moore's circle. Then we simply read values from the graph. In this example, we find that the maximum stress is 70 megapascals, and the minimum stress is minus 30. We can simply read this directly off the axis at the point where the circle crosses the horizontal axis. Where the highest or lowest point of the circle aligns with the vertical axis tells us the maximum and minimum shear stress. The maximum and minimum normal stresses that are determined with Moore's circle are labeled sigma 1 and sigma 3, and they are named the principal stresses. A third principal stress, labeled sigma 2, will only occur in special cases. Next, we can determine the angle at which the principal stresses occur. It is the angle created by the diameter of the circle passing through the center where the endpoints align to the tau xy magnitude. Based on the nature of Moore's circle, the geometric angle is 2x, the stress element angle. Thus, you have to divide it by 2. While of academic interest, there is very little that we will use the orientation angle for in our stress analysis. The angle that is complementary to the principal stress angle tells us the maximum shear stress angle. Again, it is 2x, the actual stress element value on the graph. So the application of Moore's circle tells us the maximum and minimum normal stresses as well as the maximum shear stress. We will practice creating Moore's circle in homework to give you a level of familiarity with it. However, in practice, you will never need to construct Moore's circle. You will use the principal stresses, but these can be derived mathematically rather than graphically. We'll end this video here, and in the next video, we'll talk more about applied stresses.